The previous problem we have considered is a state estimation problem that has been solved using interval analysis and applied to a localization problem. In this example, in the previous example, I have considered uh, an ellipsoid and a robot inside this ellipsoid. So I will represent it like this. And there, in the middle, I had the landmark. It was a 0 point. And I was able to measure the distance like this. The distance between the robot and 0. D is the distance. I was also able to measure the heading of the robot, like this one, theta, and also the speed of the robot. So these are the proprioceptive sensor of the robot, and the exteroceptive is T. Now what I will consider, here it will be not anymore a landmark, but a boat, like this, a big boat in the surface, and here it will be AUVs, under the water. But for this exercise number 4, I will consider them moving on the surface, so it will be a two-dimensional problem, but it is exactly the same as if I have a three-dimensional problem if these robots are moving in a plane. Okay, so the robot will move on the surface, so later what we will do, we'll have not anymore an ellipsoid, but a big boat, like this one, and two small AUVs or other boats on the surface. These two robots will be able to measure the distance to the boat, but also the distance between the two AUVs. So if you prefer, I will have three distances. D0, 1, where 1 corresponds to this robot, so we'll call them scoot. Because it will be scoot robots, they will be in front of the big robot to prevent of dangers. This one will be the main boat, so it will be the boat, and it will have the number 0. So we'll call this one maybe B, it will be the boat B. This first scoot will be the scoot number 1, and here it will be the scoot number 2. We'll have to control them with respect to the main boat. This distance will be called D02, and this one will be called D12. Okay. So in the previous example, in the previous exercise, we were able to estimate the localization using a set method. So we were able to obtain sets like this, which contain the robot in a guaranteed way. Sometimes we had some symmetrical solution, for instance, like this. It means that from the measurements and also from the state equation, we were able to conclude that the robot was either here or here. Here it will be the same. We'll have a boat moving, but this robot has a GPS. But for the scoot, they don't have any GPS. These robots are able to communicate like this. So of course the robot, the main boat, will communicate its location thanks to the GPS, and from their own state equation, from proprioceptive measurements, such as the speed, and from the heading of each robot, and with all distances, they will have to find a set which enclose the true position. So it will be the case for this one and for this one. So of course, each robot is able to communicate this direction or this direction, and the main boat is able to communicate like this. From their position, they will have to control, they will have to control their speed and their orientation so that they will stay at some uh, set value or points. For instance, some points that will be here, for instance, fixed in the frame of the boat. The captain of the boat asks the scout to go here or here with respect to the frame of the boat, for instance. And these robots will have, these scouts will have to be at these set points. Uh, so I will start with the previous program, this one. The previous program is given here. The only thing that has changed is that I have created uh, an object, a class named Scout. So it is the same program. First, I generate my data here. I initialize vibes for drawing. So here I generate some data for the true robot, and I generate in this loop the speed, and the robot has been called S1 because I will have S2 later, and S means Scout. Then I have a loop and I call Civia for localization. The Scout program is quite simple. The same as I use the Civia algorithm for localization. And the separators are given here. Okay, so let me run this program to check that it was the same as before. Maybe I have extended the noise. We can see here that I have the set which enclose all solution. So it means that the green point means the actual value for the robot, and my observer was able to prove that I am here. But due to the noise and to the symmetry of the problem, most of the time we have another set here, which also contains the solution. So at the last step, there is no problem of symmetry because I am near the origin. Since I measure this distance, the accuracy is better. But at the beginning, of course, since I had no past measurement, the solution set is a circle. Okay, the ring. Okay, so now I will start with this program and I will change it a little bit. First, I will make the robot moving, the Scout moving, with respect to some state equation. What I have to do first, I have to introduce a state model for this, and the robot will be described by state equation. So what will be this state equation? I will consider that my robot, my Scout, here, it is up, I draw like this, the frame, and here I will have the center of the robot. Here it will be X and Y. The robot will have also a speed vector v, and the heading of the robot will be theta. Okay. This is important to have. So theta is assumed theta corresponds to this, for instance, and theta is considered. We know theta thanks to the compass with a given accuracy, and the speed is known with also the speed with a given accuracy with a log, either a log Doppler or another of maybe from the propellers we have a good idea of the speed. Okay, assume that we have this. About the state equation, I will consider a classical model for the robots. It will correspond like this: x dot equal to v cos theta, y dot equal to v sin theta. I will have v dot equal to something. It will correspond to the input. So I will control it from the controller, and I will add, to be realistic, some kind of fluid friction like this one. Okay. To avoid the speed of the robot tend to infinity, I need some friction. Or it could be something else, doesn't matter. What is important for me to measure the speed and theta. This is just for the simulation. And also with my controller, I will be able to measure, to control theta dot. So it means that for my robot, for, I will have two inputs, U1 and U2, and I will be able to measure some distances. Okay, so the G, for instance, some distances to the robot or to the other robot. I will be able to measure the speed V, to measure theta. All this will go inside the controller. So the controller here, I will have some set point here, let's say W, the trajectory I want. This will be the controller, which will generate the two inputs. Now, inside the controller, there is an interval observer. So this interval observer will provide us a set, let's say like this, a set like this, and this set enclose the true value for the robot. So it will be. So what I will do, I will take an envelope for this. I will compute this using intervals, of course. From this envelope, I will take the center of this box, and I will consider that this one corresponds to an estimation for x, for the state. So for my problem, what I want to estimate, it will be, of course, x and y. So take care, x here is the state. It corresponds to what, or not exactly to the state, but what I need to estimate is x and y. Okay, because I measure this one and this one. So interval analysis is used here. With boxes, I will be able to approximate this set. Okay, I come back here and I will have to implement the observer for the initialization. So what I will do, I will have to consider here, an evolution function. I will call it maybe not here. Okay, maybe here. So I will use an Euler method, or I will call this clock move, for instance. With an Euler method, I will be able to make move my my robot, my scout. Uh, of course, to implement, I will create some double x1, so it will be the next step for xy, so it corresponds uh, theta1 and v1. So my state equation will be like this one: x1 equal to x plus dt times v times cos theta. So what I'm doing now, I'm just implementing an Euler method to integrate this state equation. I will have to declare later x and y. I have not done this, but I will do it just after. Uh, y1 correspond to this, set sign here. v1 is equal to v plus dt times. So here I have minus 0.1 multiplied by v and v plus u1. So I will have to declare all this. And the last one will be theta1 equal to theta plus dt times u2. These are the inputs. Of course, once I have this, I will have to replace the actual state. X will be equal to x1, y will be equal to y1, theta will be equal to theta1, v will be equal to v1. Uh, Now, of course, I will have to, for the initialization in the constructor, better to initialize with some. Since I implement some state equation, I will have to initialize the, the robot with some state vector. Y1, theta1, v1. X equal to x1, y equal to y1, theta equal to theta1, v equal to v1. Now about the inputs. At the beginning, I can initialize like this to 0. Okay, and that's all. Of course, in the header, I will have to declare x, y, theta, v, u1, u1 and u2. Now in the Scout class, I will assume that I don't know the true value. I do not memorize the true value for the trajectory, so I remove this. I will memorize my speed with as an interval because of the uncertainty. I can have it with a log Doppler, for instance, or with any log. I measure the theta and the distance to the boat, okay, or to the buoy at the beginning. Here in the main program, I cannot do this anymore. So I will not generate in this way. So I will not do this. And I will not do this anymore also. Okay, so I remove this. In the declaration of the Scout, now I will have to initialize with, say, -1, for instance, 2. So it is for x and y. Or here I will put theta, so it will be 3 and 1, whatever. So here it is for the speed. I will in the loop here, I will insert. So this one will not work anymore. I will write, let's say, s1 dot s1 dot clock move is not declared. So I will have to insert this one in the header. Let's say here. So it will clock move. Good. I will avoid to call CVA first because I have no measurements. I will draw here, this one does not exist anymore, but I will be able to draw X and Y. Also for the initialization of the Scout, here I will have to be consistent with the header. Okay, I will try to run this. An error. Of course, I don't need this. Compiles. And here we see the trajectory of the robot and the 0 point which corresponds to the boat. To check my state equation, I will maybe change the initial condition, maybe the input also. So here, for instance, I will start with -1, so the robot will turn right because it corresponds to the indirect direction. Then maybe for the in the main, maybe I can change and put let's say 2, 0. Okay, just to change the initial point. compile. So it's a good trajectory for localization. So now I will be able to call Civia for the localization. But first, I have to uh, maybe to declare or to define the, the distances. So here I will do double D01, which corresponds to the distance between scoot number 1 here D. So D01 will be, for instance, declared here for Civia. It will be computed here. D01 corresponds to iPod. So it will give the norm, iPod of x and y gives the norm of the vector of coordinate x and y. So here I will have the distance to 0, so it will be s1 dot x, s1 dot y, and it is what I measure. I will add here plus random of epsilon, so it gives me takes a real number, a random number inside epsilon, which is defined here at the top of the program. Okay, here it's small d. And there I will have probably to make to tell this to the observer, so to the scout. So I will send this information to the scout. So I will call, for instance, a new function s1 dot. So I will here I will do not a clock move, but maybe a clock store, and clock store will store all available data, and I will send this. I will send okay the coordinate of the boat. So the coordinate of the boat is 0, 0 at the moment. I will send here D01 plus the interval epsilon, which is an interval. Of course, I will have to define this inside the program. Okay, back to Scott, and maybe I can put this here. Void Scott, and this will contain so double the coordinate of the boat x that are sent by the sound between because there is a communication between the boat and the robot, but at the moment, of course, this corresponds to 0, but later the robot will move. And here it will be an interval which corresponds to the distance. So I will call it, for instance, distance boat 1. Good. Okay. So store what I will memorize everything boat, but pushback. So I memorize everything. So I will use a pushback of boat 1. I memorize it. I will also memorize some other quantities, such as the boat. Boat x dot pushback of boat x. Same here for y. I will also memorize all proprioceptive measurements. For instance, v dot hop, pushback. Excuse me. Pushback is like this normally. Okay. Pushback. Here it will be the speed, so it will be the actual speed plus an uncertainty, so I will add a noise, random of epsilon plus the interval epsilon. So I'm sure that the actual value v will be enclosed inside this interval. Excuse me. And I will do the same for the compass. Theta. Okay, so it will be theta, the actual value theta, plus I add a noise, like this. Okay, so here it is not happy maybe because these have not been declared. And I will declare them here. Okay, so I will need to add, so dbot exists, vote x and vote y. Okay, so store, memorize everything. Uh, so here it is not happy because of this, probably. And there, so I was able to measure everything. Now, Sivia could work. Sivia is given here. And I run the program. This one is not a member. So I declare it. Here, capital S. So we can see there is I always contain the true position. We can see that the dot points are inside the yellow boxes, but it's not accurate at all. Uh, Probably because there is a lot of ambiguities, and I will have to find a way to avoid this. So the idea is the following. When I know at time, for instance, when I know at time k, I am here because I measure the distance. I know that I am here. And then, because of some measurements at time k plus 1, I obtain this, which corresponds to this one that is moved because of the evolution function, but I also obtain some other solution because of the symmetry of the problem. Since I know that time k, I am here, at time k plus 1, I cannot be there. So how can I avoid this? I will compute at each time a box which encloses this set. I will compute the image thanks to the evolution function of this set, and I will perform my bisection, my research inside this box. So I will not compute this one. It will be more realistic. I will create a box E at time k, and I will compute thanks to phi k plus 1. I will be able to compute this one, a of k plus 1. And all my bisection will be inside this box. That's what I will do now. Uh, I go there. I will build a box inside Scout, and I will call it E. This box will be initialized in the constructor equal box, and at the beginning I know that I am inside the interval, let's say minus 10, 10, minus 10, 10. In the CV algorithm, I will do this, E. Okay. So at this level, it does not change, but I will do here compute the next E. Clock next. And the next E will be computed here, so there is no inputs. And there I will the new E equal to phi, the transition function, E k plus 1. Okay. And I can draw it using vibe, for instance, E dot draw box, and in green. And of course, I have to call this function, and I will do this in the main program. S1 dot clock. Clock next does not exist yet. They have to declare it in the header. In the CVA, of course, I have to compute the enveloping box E from the beginning. It will be the union of the generated paving. To have the union, I have first to initialize E to the empty box of dimension 2 here in my application. And At this level, all yellow boxes will be uh, will have to belong to this box. So I will do here E equal to the union of the current box X, which is yellow, which is the frontier of my set, with X. There is also one. Okay. You should note also here I only call the separator with 1, not with 0. It means that I don't want to compute the inner approximation now, only the outer approximation. Why? Because when I will make the robot communicate, the meaning of the inner set uh, is not clear. I mean, when I will have new information from other robot, a point which was inside is not, can become outside. That's why I can only consider an outer approximation. I compile, and I can see here now I have a much better enclosure. Okay, it means that I know that my state is inside. Now I am able to localize in a reasonable way, and I will be able to perform my control. Okay, now I will have to make my boat moving. I will add a new class for the boat to make it moving. File, uh, new file or project, choose, boat, next, next. Okay, the boat is now here. Uh, I will try to copy what I have done for Scoot. Okay, so I can include this, the global variables, some initialization. Okay, include debug, Scoot I don't need it, Vise maybe, extern DT I will need it, this one I don't need it, probably this one. Okay, so now the boat will have state, a state or state equation. I will copy this one to influence. Okay, so I will call it boat clock move also, or clock. It will be I will take the similar equation except y1, y2, v. Okay, yeah, I can take the same equations. Okay. Now for the initialization, I will initialize the state as follows. For instance, 0, 0, y equals 0, theta equals 0. The speed, let's say 0 for beginning, or 1. The input will be 0, and u2 equals 0. I don't need k here. I don't need this also. I will use this to declare in the boat.hash. The clock will be here, and I will declare double x, y, theta, the speed, u1 and u2. In the main program, I will also declare, so I have to declare the boat. So I will have to include boat. I declare Scout and the boat. I will call it B. And here I will put B dot propose me clock. Of course, the distance now will be the distance between, so D dot X, the boat X minus and B dot Y minus. So now I measure this distance, and I will make the boat moving. I can remove this. Also, if my boat is moving, the distance here should correspond to boat x of k2. And here, okay, so here it will be the distance to the boat. But now the distance to the boat is assumed to be known. That's why probably here, yes, here I should put not an interval, but a vector of double. This one, because they are known. When I call zeros here it should be, of course, b dot x, b dot y, the coordinate of the boat. I will draw also the boat here, so x and y in red, and I will see the boat moving. I compile. We see the boat moving red, and the estimation is correct. But of course, there is some singularities when the two go in the same direction. So we'll see later what we can do for that. I will change a little bit the motion to check that everything's okay. For instance, here I will move the control of the boat and I will say that U2. So maybe I will not, I don't need this. So that I will not have to control it, the speed will be constant. And I will say that something like 1 plus sine of 0.1. So it means that the boat will always turn, this will be always positive. It means that the boat will always move left, will turn left, and I will put here a small coefficient like this one, which is important because it will not be a circle and I will see some different behavior. When this one will be almost zero, the robot will be straight on and the accuracy should be, okay, we'll see later, but it will turn and does not go straight. Okay, I compile. Okay, so the robot is moving, turning left. Okay, so there is not so many differences, but later for longer simulation, we'll see some maybe more different situation. Now what I will do, I will add another robot here, S2. I will initialize maybe -1, 2, heading 0, speed 2, for instance. And there I will have to compute the distance, T02, which corresponds here, it will be 2 and 2 for the scoot number 2. I will have to send the scoot number 2 the information on the position of the boat and the distance that is measured. I will be able to ask for a CVIA. I will move the scoot number 2 and maybe, okay, I will draw it in another color, let's say blue. So now I will have two scoots. An error. T02 is not declared. Of course. Okay, here. Yeah, of course I have to do the same, the next for S2. It compiles. It works. Whoops. I don't know what. Okay. So it works. And we can see that I always enclose the true point for the blue scoot and also for the green one. Okay. So now what I will do, I will have to build the controller for the scoot. I know the position of the scoot. I have a good approximation for the scoot, and I want to build the controller. So I will do this here. So here it will be something like clock control. So what do I need for the control? I want to have the position of the boat, let's say boat X, X and Y. It is important also to have the heading of the boat. I know this because of the compass I have on the boat. Maybe it would be nice to have the boat theta dot, so the rotational speed of the boat, the speed of the boat, also the waypoint where the scoot should be, say be like this, so the position of and also for Y. So it is the position of where the scoot should be in the frame of the boat. Okay, so now maybe like this. Uh, oh, there is a mistake, but I do not see it at the moment. Maybe later. Okay, now what I should do, I will have, I know, I have an approximation of the position of the boat. Double px is this approximation. It will be the center of the envelope. So it will be the same for y. So px and py corresponds to an estimation of the position of the boat, of the scoot, in the frame of the boat. So this is, if you want, the estimate position of the scoot in the boat frame. Now I want this scoot go to a target. So I will call the target Qx and Qy. So Qx, uh, I will need to show how it is computed. So assume I have my boat, the main boat, which is here. I have my scoot, which is here. My boat is moving, so it has a speed like this. It has a heading, and it has a rotational speed, theta dot. So in the frame of the boat, uh, a given point, moves like this, because this one is turning. Okay, this one moves like this. So there is some kind of vector field which represents all points of the space moving with respect to this frame. Okay. I want my scoot be here. So here it will be the point Q. My scoot here is at point P. What I can say is that in the word frame, Q is equal to in the word frame. So like that, it is a word frame. So Q will correspond to the coordinate of the boat. Let's say B. It is a point B plus a rotational matrix cos theta of the boat. Okay, theta boat, P boat minus sin theta of the boat sine theta of the boat cos theta of the boat multiplied by Q in the frame of the boat. So in the robot frame, robot, the boat frame. So here it is in the word frame, and here in the boat frame. Now it is what I will program now. So Qx will be equal to Vx plus cos of V theta multiplied by Qxv minus sine of V theta multiplied by Qyb. The same here for Qy, Vy plus sine V theta plus. Okay, now I have the coordinate in the word frame. So to check it, I need to draw it. So I will draw a square with Qx, Qy. So here it will be the diameter, 0.1. So it means no, the orientation. So it will be okay, a square or losange, and I will draw it red. So this is the set point in the word frame. Now I need to compute the vector which corresponds to the error to this. So it will be E. E corresponds to Q minus P, and it is the error. Now I will try to compute the derivative of Q, because of course, when the robot is moving, Q dot will also move. So, for instance, if the robot turns left, here Q dot will move like this. So even if it is fixed in the boat frame, in the word frame, Q dot will exist. Okay, so I will have to compute it, and I can write it here, Q dot will be equal to the speed of v, so the speed of the boat, multiplied by the vector cos theta boat sine theta boat. So this vector corresponds to this vector. Okay. But because of the rotational part here, so let's say this rotational part, I will have to write here to add plus. So a vector which is orthogonal to this one will be theta dot of the boat minus multiply by qy minus the boat y. It is the y of the boat. And here it will be theta dot b, so the rotational speed of the boat, qx minus vx. Okay, so it is in the word frame, this one. So I will have to program it. And then I would like P to follow this. So, then I will move P with respect to Q, to the error between Q, but also with respect to Q dot. It corresponds to a proportional and derivative control. That's what I will do. So if you want, the vector I would like to follow for this one will be a mixture between the distance in the range, but also I have to follow Q dot. It is a proportional and derivative control. That's what I will program here. So double Ex equal to Qx minus x. The same for y. It is error. Double. Now I will have Q dot x. It will be, so I have, as I have written here, Q dot will be Q dot x and Q dot y. So Q dot x will be equal to the boat, the speed of the boat, multiplied by cos of theta, the heading of the boat, minus b theta dot multiplied by qy minus by. And here the same for y. pv, here it's sine. Here plus qx minus x. Double, so I will call it w. So w x corresponds to what I have written here. It is that, so w is here. It will take into account this, okay, but also this. So proportional to go toward q, which take into account the error, but also derivative, which take into account the derivative of the error. So wx q dot x plus, let's say, 0.2 or a small coefficient multiplied by the error. W, excuse me, here equal q dot y plus 0. Now I will draw an arrow just to see that I do not make to represent that everything is okay. Px, Py, Wx, Wy, so the desired direction. 0.1 is the coefficient for the shape of the arrow, and let's say green. Now I will compute the speed. So d'abord, W bar. So I will compute the vector W, so the heading, the direction of W, and the magnitude of W. So it will be here V bar, so the desired speed for my boat, for my scoot, will be equal to the I pot, so, or to the norm of W. And the desired rotation will correspond to the angle corresponding to V. So it will be VR. Excuse me, no, it is minus V. So here it is the error. V bar is the speed I want, and V is my actual speed. This is the error on the speed, and I compute R tangent so that I will have some kind of proportional control with the saturation. Double, so it will be theta bar, which will be equal to the angle of W. And the rotational speed I will give to the scoot will be equal to R tangent. So it's some kind of proportional control, but on the heading to avoid the 2p problem. Theta R minus theta divided by 2. So this is a proportional control. And this expression with R tangent of tangent is just to avoid the modulo 2p problem. So, minus theta divided by 2 is divided by, okay, like this. Okay. Okay. Proportional control. This is my control. Of course, this one should be declared. And in the main, it should be called S1 scoot1 dot clock control B, the coordinate of the boat, P dot Y, P dot theta. This is P dot U2, so the rotational speed corresponds to U2. Here it will be the speed, and the coordinates. So let's say 3 and 2. So it means, the 3 and 2 means at my boat. Okay. My boat is like this, the main boat. I have my in the robot in the boat frame I will have X and Y. If I want it to be when I say 3 2, it means that it corresponds to 1, let's say 1 2 3 for X and 2 for Y, so it will be here. So the first scoot should go to this target point. And the other one, if I want, for instance, 4 minus 2, 4 minus 2 will correspond to 1, 2, 3, 4 for X and minus 2 here. So in fact, I want one scoot to go there and one other scoot to go here. Okay, so at the moment, I did not take into account the distance between the two of them. This information will be used later. Okay, so I only measure at the moment uh, this distance and this distance. Okay, so let me come back here. For the scoot number 2, I will do a similar control, but I will say, for instance, 4 minus 2, as in the picture. Here, for instance, for 10 seconds, I run this. So my scoot should go in the target points here. Whoops, sorry. So this one will go there, and the other one is trying to go there. The main boat is here, and the targets are represented by the square. The green arrows correspond to the direction where the scout wants to go, and indeed, he wants to go to the target. As we can see, there is some singularities, and this set increases a lot, which can be dangerous. So I will take into account this distance between the two scouts in order to improve this accuracy. Alors, dernière étape, on a notre bateau numéro 0, le scout numéro 1, le scout numéro 2. On a déjà traité l'information où on mesure D01. Ici, on a mesuré D02, donc cette distance-là. Et on n'a pas traité le fait qu'on mesure aussi D12. Donc là, il faut bien comprendre que les calculs sont distribués. C'est-à-dire que le robot qui est là, donc le scout, va calculer un ensemble, alors que je représente, mettons, comme ça, qui contient sa position, uniquement en prenant des 0,1. Alors ça, c'est ce qu'on a fait actuellement. Pareil, de son côté, lui, le scout numéro 2 calcule sa position. Contrairement à ce qui se passait avant, c'est qu'on ne peut pas véhiculer par Wi-Fi, ou enfin par le son, autant d'informations que cet ensemble. Donc, contrairement à tout à l'heure où celui-là communiquait sa position qui était calculée par le GPS, ici c'est pas le cas. Donc, on va essayer d'envoyer une sorte de résumé de ça. Alors, pour avoir le résumé, ce qu'on va faire, c'est que ce robot-là a calculé à l'étape numéro K, va avoir calculé une boîte. De la même façon, celui-là va avoir calculé une boîte englobante. Alors, cette boîte englobante, c'est ce qu'on a appelé ici, alors on va l'appeler grand E1, et cette boîte-là, ça va être grand E du Scout 2. Ces boîtes vont être envoyées par le son, ce qui est possible, et grâce à l'information que va obtenir E1 du Scout 2, et grâce à cette distance, il va être capable de contracter cet ensemble-là. Donc après, cet ensemble-là, il va obtenir quelque chose de plus petit, grâce à D1,2. De cette façon-là, il va obtenir une boîte à nouveau plus petite, qu'il va être capable d'envoyer aussi de cette façon-là. Lui va être au courant d'une boîte. Alors, lui, de la même façon, il a été capable, de son côté, de calculer, grâce à la boîte noire de E1, a été capable de calculer un ensemble plus petit. Et donc, il a été capable de calculer aussi une boîte plus petite, parce qu'il a pris en compte la boîte noire de 1. Et ça, il va pouvoir l'envoyer comme information à E1 par le son. Et le processus continue. C'est-à-dire, grâce à cette boîte rouge rétrécie, lui il va être capable d'obtenir un ensemble plus petit, de même lui une boîte plus petite, et donc, alors là je dessine la boîte plus petite, mais ça on va pas pouvoir le faire 36 fois. Mais on va le faire à chaque instant d'échantillonnage, on va peut-être essayer de véhiculer plusieurs fois cette information, et donc l'ensemble du processus peut prendre moins d'une seconde. Bon, on va essayer de le faire ça. Par exemple, on va le faire 3 fois. Bon, on aurait pu le faire qu'une fois ou 2 fois, mais on est obligé de raisonner comme ça du fait que le calcul est distribué. Voilà. Donc, je vais reprendre, je vais donc revenir à mon programme. Et qu'est-ce que je vais... Alors, au niveau de mon programme, je rajoute maintenant le fait que je mesure D1,2. Ici, pareil, je le déclare. Ah bah, voilà, bon, il est déclaré ici. Maintenant, ici, je le calcule. Alors, lui, pour le main, il est au courant d'un peu toutes ces informations-là qu'il va distribuer au robot. Alors, que vaut D1,2? C'est l'hypoténuse de... Alors, ici, je vais avoir S1.x, S1. Donc, ça, c'est la vraie distance. Je lui rajoute un bruit. Ensuite, ici, au niveau clock store, qu'est-ce qui va changer? Je vais envoyer BY. Ça, bon, actuellement, ça ne change rien. Ici, au niveau du Civia, que je vais lui envoyer cette information. Donc, je lui envoie D1,2 plus epsilon, donc un intervalle qui contient D1,2. Et j'envoie cette distance. Et je vais lui envoyer aussi la boîte englobante de S2. Hein. Ici, de la même façon, à S2, je vais lui envoyer cette distance avec cette incertitude, mais la boîte englobante pour S1. Donc la S1, je lui envoie la boîte englobante de S2 et réciproquement. Et ça, je vais le réitérer plusieurs fois. Bon, alors, pour commencer, comment je vais peut-être faire for. Alors là, ça dépend du temps. Mettons, parce que ce temps est limité, surtout pour la communication. Le temps de calcul n'est pas trop gros, mais c'est plus le temps de communication. Et tout ça doit se faire de façon instantanée. Donc, for int, alors là, je vais peut-être le faire for int égale 0. Alors, je vais le faire 3 fois. A plus petit que 3, A plus. Et je vais faire Cécivia, et là, j'ai une résolution distribuée de mon problème d'inversion sans liste avec l'échange d'informations entre les robots. Alors ici, de la même façon, mes robots, je vais les dessiner un petit peu mieux que par des points. Je vais utiliser la fonction draw robot qui admet B, alors BX, B, BY. Alors Bθ, ça c'est pour le bateau principal. Excuse me, I have to speak English. Also, I have B.U2. Excuse me. I don't need this one. Just to draw it, I need 0.1 would correspond to the size of the robot. The color, red. Okay, this. So this is for the main boat. And I have to do the same for the two scoots. So for the first scoot, here it will be S1, S1, maybe smaller, for instance, 0.5, and the color will be, say, black and green. The same for the scoot number 2, S2, 2, 2, and here maybe another color, cyan. Okay, now I perform the. Okay, I move this one here, the same. Just okay, the control, move. Okay. Now, probably here in the Civia, I send an interval and the envelope. So I have to change this in the main in my program. So it will be here. Civia is here. So now I will have the interval. So this one corresponds to the interval. But body. So body, the other robot, the distance to the body. Okay, so it corresponds, if you prefer, to, I can write, okay, the distance to the body. Here it will be a box. So box, and this box corresponds to the enveloping block box of the body. Body is the other scoot, and this is a constant. Okay, now I have to initialize here to say that E body, so I have to memorize it, equal to E body 1, and the distance, because the distance to the body is equal to D body 1. Okay, now what else I should, so I memorize it here, and there I have to change in the declaration of the CVA. Scoot.hash here, okay, and also in the CVA, now I remove this draw row, I don't need it anymore. In uh, in the CVA algorithm, I will take less boxes. For instance, instead of 1000, I will take 20 because of the computing time. Uh, Also, my separators, I have to change because at the moment I only use ion in my CV algorithm. I use the separator, which is given uh, here. Okay. So this one I will replace. I have to take into account also the distance between the two robots. So this one I will replace by uh, a separator. I will call it contract. Contract XNK. Okay. In contract, I have to build it here. So void, scout, contract, and there I have to provide a box, and an integer corresponds to k, k1 say. Okay, this one calls the previous separator, but also another contractor. So it is a contractor because of the one which is here. So I call the separator as a contractor. And there I have to take into account the distance. to the body. So I call it like this. And there, okay, so I take the two into account. But the distance to the body, I have to program it, let's say here. So the distance to the body will be this. I send a box, and this one I don't need it in the contractor. And there, I call a contractor. So box, I store it in a box A equal to e body, the enveloping box of the body. Interval R corresponds to the distance to the body. And there, I call a contractor C distance with R, x of 1, x of 2, a of 1, a of 2. Okay. Uh, Now what else? Probably I have an error here. A of 1, a of 2. So I don't see at the moment where is it? Where is okay? It's here. Okay. Now what is this one? C distance is inside the interval library, which use ibex. I have plenty of contractors, basic contractor in EasyBex, and this one use ibex in order to take into account the fact that the distance between x1 y1 and x2 y2 corresponds to r. So this is the equation used by ibex in order to contract x1 x2 and y1 y2. So here in the CVA, I had to store it. I had to store it in some intermediate variable in order to avoid to contract this one, which could not change when the CV algorithm will bisect boxes. So when X change, this one will not change because it is the enveloping box of the body. And since this one will change R and A, but I am not allowed to change E body and D body. That's why I had to store them somewhere. Uh, I compile an error. Of course, this one have not been declared. So I declare them here. Compile once more. Okay, here small c. Okay, so this has been taken into account. The accuracy is a little better, and I can run the simulation. So at the beginning, of course, the accuracy is not very good, and after later, it becomes much better. Okay, but it increase. Sometimes it increase. In the control, I have to react somewhere. So what could I do? For instance, I will ask one of the scoot when the accuracy is too bad to maneuver just for localization to avoid this. So in the control algorithm, I will do something like this. If the width of the box E larger than 2, fine. Then I will take U1 equal to 1. So it means that it will turn left. Okay. So if the accuracy is bad for the localization of one robot, then it will maneuver something stupid, and it will turn left, just in order to have a better localization to avoid the singularities. When all robots go in the same direction, I have a singularities. So let me maybe explain why. When I have, I will draw my robot here. I assume that I have my robot like this. Okay, so the main boat will be here, for instance. And one of the scoot is here. And the other scoot is there, for instance. What will happen is that I measure a distance, and a distance, and each of the robots goes straight, the same direction. Then I cannot make the difference between another situation, which is like this. One robot is here, one robot is here, and I measure this, this, and all goes to the same direction. Uh, it means that I can go from this triangle to this triangle by a transformation, by a rotation and translation. So all distances will be the same. So what happened? I will ask one of the robot, for instance, this one, which the one which has bad accuracy. For instance, let's say that this one is known to be here, and this one is known to be here. Because the inaccuracy is too large, then I will turn left. I will avoid the singularities and have a better localization, and this will be transmitted. So I will have something better just later, and this will be transmitted later to the other scoot. Okay. Also, the last step, maybe I will take larger time, maybe 100, like this. I compile. So up to now, the size is not bad. So there is nothing to maneuver, but the inaccuracy increases. Of, but here it's almost a singularity. it increases. Oh, this one maneuver. Look here. Because it was too large and now he has a better localization. Look here. It was bad. Now it's much better. And this has been transmitted to the other robot, which has now a better accuracy because of the communication here. So because he maneuvered, it was able to localize better, and this has been transmitted to the other.